There is a cubic formula, believe it or not, but it's nasty. And so a lot of the time what we'll do is we'll use some best guess type practices to narrow down, like what's one thing, at least one thing that we could get that would make this thing equal to 0. And we'll help you to narrow that down or whatever. And then once we can get one of them, we can reduce this problem into a smaller one. So check this out. Okay, rational root theorem says that if I were to guess, like, we're just guessing right now. I want this to all equal 0, and I'm guessing, like, what number can I plug in for x everywhere here that will make it equal 0? Not easily found. Because you could just guess anything, do I put 20 in, or -7, or, what should I put? But there's one result that would suggest that we can at least narrow down the process a little bit. It's called the rational root theorem. And it says this, if you look at the 15 and you look at the 12, not every root is found here, but the rational roots, hey, I'm having a focus issue, but the rational roots, which are, things that'll zero this out, that are rational numbers, hey, come on, focus, do it. We'll just, how about we just do blurry math? That'll do it. Okay. Forgot what I was going to say, guys. I remember now. So, rational root theorem, if we're going to find rational roots that are rational numbers, I can at least narrow them down by saying this. I know they're going to come of the form of things that go into 15 over things that go into 12. They'll be either a whole number or a fraction of that form. So we'll take the 15, we'll take the 12, and we'll play with them for a second. Check this out. The last number in the row is a 15, so we'll say 15. And then the first number was a 12. And we'll just start listing things that go into 15 and things that go into 12. And we'll put one list on top of the other, basically. And so things that go into 15, that's like, 1 goes in, 3 and 5 and 15. I think that's it for 15. And then for 12, it has a little bit more. We have 1, 2, 3, 4, and 6 all go into 12, as well as, of course, 12 goes in. So there's a lot more that goes into 12. And then the theorem would state if you want to start guessing numbers to plug into your function to hopefully get a 0, it's going to be one of these over one of those as a fraction. I tend to like to try the whole numbers first because 1 over 1, that's maybe a golden goose to try for. Like, who wants to try fractions first, And so 3 over 1 is a good one to go to, then 5 over 1, and then 15 over 1 is a whole number as well. If none of these work, then we'll start trying the weird ones like 1 over 2 or 3 over 4 or something. 3 over 3 is not bad, but that's already a 1, so that's not going to help. Anyway, we'll try some of those if we need to, but really right now we're just going to try and find one good root that works. Hopefully we can find a whole number one. Something to plug in that'll make this thing zero out. And if it works, then we'll be able to reduce the problem down to easier ones after that, because then we can turn it into quadratic by some cheater's technique. So check this out. Let's try a 1 or a 3 or a 5 or a 15. We're just going to shoot it into the function. And there's other ways to do it too, of course, but we're just going to shoot them in for now. And so we have 12x3 minus 19x2 minus 56x plus 15. Actually, what we could do, what a lot of people do, is that instead of plugging it in, because then you're trying to do like, imagine if I had to plug in 15. 15 to the third power is a nightmare. So another quick way of doing it is to remember, okay, so this is where it gets deep, but I'll try and give you a quick take, because this is quick take homework, and this is already dragging on a little bit. So say we found out that that 1 is a root. What that means for us is that if 1 is a root, then we would have that also out of this mess, then x minus that 1 is a factor of the whole thing, because it would be like x minus 1. You know how we do this. This is a degree 3 polynomial, so it would be like degree 1, degree 2, degree 3, and we'd have maybe 3 linear factors if we were to put f of x in factored form. And if 1 ended up being a root, then that means x minus 1 is a factor of this thing, because then 1 minus 1 would be enough to make it zeroed, And so the reason I bring that up is because if that's the case, then that means that if I divide this whole mess by x minus 1, be it by long division or synthetic division, then the remainder should be smooth because the leftovers will be perfect factors as well. And I mean, without getting totally into it, it means essentially I can get away with dividing this by x minus 1 and expect there to be no remainder. And if there is a remainder, that means this is not a factor in the first place. That's the short way to say it, I guess. And so what we're going to try and do is we'll just divide this thing by x minus 1 and see if there's a remainder or not. And if there's no remainder, then 1 must be a root, and x minus 1 would be a factor. Let's see how this goes. Let's try 1. And so, remember, dividing by x minus 1 in synthetic division is you're going to switch that minus 1 back into a plus anyway. So you can really just go by the original list because your minuses will be turned back into the other ones anyway. And so then, oh, I forgot to tell you guys, there's a big plus and minus up here because it could be a 1 over 1 or a negative 1 over 1. Oh, that's worth mentioning. Okay. So then I guess we have more whole numbers we could try. We could try 1 or negative 1, 3 or negative 3, 5 or negative 5, 15 or negative 15. And if none of that works, then we'll try some fractions. That sounds terrible. So let's find one fast. Okay, so by synthetic division, that'll speed up the process. We have 12, negative 19, negative 56. What else? Oh, shoot. 56, negative 56, and then 15. All dividing out that, we'll say 1 this time. We'll see if it comes out with a remainder or not. Drop the 12. 1 times 12 is 12. 19 times, or negative 19 plus 12 is negative 7. Times that by 1. Then negative 56 plus negative 7. Negative 63, I think. And then, whoops. And then 1 times negative 63 is negative 63. 15 plus negative 63 is something, but it's not 0. You know, it's got a remainder on it. If this adds up to 0, then you have a no remainder. This one does, so that's not going to work. So let's try another one. What if we tried, okay, so 12, negative 19, negative 56. Yes, it's this tedious, and that's why we're going to try and find one fast. And then 15. Maybe 3. Let's try the next one. Without trying any negatives, we tried 1, and then let's try 3. So here we go. Oh, shoot. Okay. Drop the 12. 12 times 3 is 36. Negative 19 plus 36 is something. Let's see, that's 17, I think. And then 3 times 17 is 51. Yeah. And then negative 56 plus 51 is negative 5. 3 times negative 5 is negative 15. Look at that. Negative 15 and 15 makes a 0 remainder. That means 3 is a root for us. And that means, or x minus 3 is a factor of the original. And that's wonderful for us because what that means is, not only did I find a root, I'm going to go ahead and keep that one. So celebrate that. We'll keep the root. But also what it means is what you have down here is the leftovers of after you would divide it. Because remember, we're talking about dividing x minus 3 is really what we're doing. So after I divide that out, what I have here is the leftovers. So that was x to the 3, I think, with the 12. And so then this 12 is x2. What is it? Plus 17x minus 5, and then no remainder. This is the leftovers. This is everything that's left after I divide that x minus 3 out. And so now what we have is, if I can just figure out how to solve this thing for 0, then we'll have the other two zeros, because we already got one of them. One of these roots is 3. The other two roots will be whatever I can plug into this equation that'll make it equal to 0. And that's easier because it's quadratic. And so now you got options. If we want to solve this quadratic, we can either do it by factoring, if you're good at factoring, or you can do it by quadratic formula. But essentially it all comes down to, let's do 12x squared plus 17x and then minus 5. Let's equal it 0 like we do and figure out what the heck x is can I plug into this to make it equal to 0? And again, if you're good at factoring, do it that way, or if you just prefer the quadratic formula, that'd be fine. And I'm not going to finish this part with you, but essentially it's just x equals, and then you can do the quadratic formula, negative b plus or minus square root b squared minus 4ac all over 2a, and then you get two answers out of that, x equals something and something else. Sometimes they're nice looking, sometimes they're ugly. I think these ones end up being fractions, This is not m and w, these are scribbles. Anyway, they represent numbers that you get when you plug this junk in, and that's kind of my take on how this goes. So we'll have roots of 3, and then two other probably fractiony looking things you'll be looking at, And that's how the cookie bounces with this stuff. Numbers 13, 14, 15, 16, they're same kind of stuff. Some of the answers get uglier over time, it looks like. I think, some of these, you'll be able to take a good square root, and some of them you won't, and so the answers end up getting uglier looking over time. But it ends up being the same kind of process. Giddy up.